Ooh, I'm live. Take your seats, everybody. This is a big room, I like it. All right, if you haven't heard of me before, I'm the crazy plant lady. I'm not afraid to admit that. So if you're here for the plant talk, this is the right talk. So here's a little bit of proof. I feel like I need to back up this claim that I am the crazy plant lady. So these are some of my plants. These could be stock photos, though, so further proof is yesterday I went and found this, plant warp. Isn't that great? I went and looked at all the plants. It was beautiful. Anyway, so I have a lot of plants. I have about 3 or 4 dozen in my home, which is entirely too many. And they keep getting bigger. It's that weird thing about plants. So they're taking up a lot of space, and they're a lot of effort for me to keep track of, especially because I travel a lot for work. So who's taking care of them right now? But that's besides the point. So actually, no, that is the point. So here, I'm usually pretty good at taking care of my plants, but in reality, a lot of them end up looking like this. And how many of you have houseplants? Yeah, that's the real motivator for you being here, right? And so, for those of you who didn't raise your hands, this is not what they're supposed to look like. This is a very depressed plant. Shouldn't be that droopy. So, this was a result of, after the pandemic and I started living my life again, I wasn't just at home 24/7. I went into the office, forgot to water this plant, and came back and just screaming for help, really. And so I figured, travel's gonna pick back up. I need to find a way to monitor my plants, at least remind myself that I needed to take care of them. They were relying on me, right? So I asked myself, is there a better way to be doing this? Rather than stressing out all the time about my houseplants and wondering if I'm going to neglect them and forget to water them, I needed some way to help me monitor these plants just a little bit better. That's not the right question, though, okay? I could go out and just buy a pre-made solution, can't I? Amazon has like 400 of them, okay? I could buy some pre-made solution to monitor and water my houseplants, but I'm an engineer. Many of you are. You're at least curious about building something on your own, so this is a better question. Is there a more interesting way? Absolutely. So, in addition to being the crazy plant lady, I am a developer advocate. But before that, I spent a number of years building out streaming data pipelines in Kafka streams. And so with Apache Kafka. And so when I became a developer advocate, I decided that my only goal, if I was going to build out a streaming data pipeline, was that it had to be useful and motivating for myself. And so here, I had this problem. I needed to be able to monitor my plants so I could keep track of them a little bit better. This is something that I would like to do in real time. So I could use Kafka, and I'd always wanted an excuse to do something with hardware, get a Raspberry Pi and maybe expense it. I did, and that was great. So this was the perfect storm, right? This was everything that I wanted in a project, and so much more. It's beautiful. So this is the perfect opportunity for me to build an event-driven pipeline in my own home, because why wouldn't you do that? And actually solve a problem for myself. So let's talk design. Pretty simple. All I wanted to do was monitor my houseplants. When I was first building this project, I was renting, and so setting up a bunch of pipes and reservoirs to water the plants was out of the question. Okay, so I figured at the very least, if I could tell myself when I needed to care about some of my plants, that was going to take a lot of stress off my mind. Okay, so I'd have my Raspberry Pi, I'd have some soil moisture sensors in each of these plants, and I could gather the moisture readings at some interval, throw that into Kafka. Okay, so that'll be happening at real time. But that's not good enough. I need a little more information to actually make sense of those readings, and so this is where the very hand-wavy data set comes in of metadata. We'll figure out what that is, but when we get to it, we'll throw it in Kafka. Okay? So with those 2 data sets in there, then we'll do some zhuzhing, some stream processing, and at the end, I wanted to receive an alert. But I'm really lazy, and so I want it on my phone, okay? And I don't know how many of you are familiar with Telegram. We'll get to that later, but I figured I would send it to my phone via Telegram. So yeah, sounds good. But at this point, I've mentioned Kafka more than enough. How many of you have used Kafka? Okay. Decent amount of you. Put your hand down. I know you know Kafka. Okay. But for the rest of you who did not raise your hands, I want to make sure that we're all on the same page here because it's kind of important. It's the backbone of this system. So Kafka is a distributed event streaming platform. I could leave it at that. 3 simple words, really. The platform part doesn't matter. It's distributed event streaming. Those are good ones. That's as concise of a description that I can boil it down to, but there's a lot in those 3 words. So we're going to unpack it. So first and foremost, Kafka is a streaming platform. It's the direction we're heading, right? We're undergoing some changes in how we work with our data, how we store our data, how we process that data, right? We're moving away from slower systems, batch-focused systems, to something like stream processing, right? We want our data to move as it's being generated as quickly as possible in real time, and we want to be able to react to that data, right? So there's a lot of technologies that can help you do this, that can stream your data. Kafka is just one of them. But generally, there's a lot of cool things that you can get out of that. Okay? You're going to increase the accuracy of your data and results in most cases. You're going to make your system more reactive, definitely. And especially in the case of Kafka, you can actually make your system more resilient. So Kafka is a streaming platform. It does this for you. It enables you to stream your data from A to B if you want, and do more stuff on top of that. So it can be just a messaging layer. It can serve as pub sub, a persistent storage layer if you want Kafka to be a database. That's weird, but you could do that. And you also, as we'll get to later, we can use it. There's some processing tools involved in the Kafka ecosystem that helps you do processing. Okay, so it's a streaming platform, but it's also an event platform. So if you take nothing else out of this, those of you who did not raise your hands saying you knew Kafka, this is the only thing that you are required to take away with you, okay? Besides the plant part, store that away, because that's important about me. But in order to use Kafka successfully, you really need to start thinking in events. It's so, so critical. It's going to affect how you design your systems, how you work with your data, how you think about it, okay? And I don't want that to scare you. Start thinking in events. It kind of sounds like I'm telling you to rewire your brain, but you really don't have to, right? As users, as programmers, as humans, you already know how to do this. Just pay attention to it. Every time you submit forms online, every time you look at application log files to debug something, every time you get a notification on your phone, those are all events. Okay, so you are constantly being inundated by these things that are events, and you know how to work with them. They're not frightening, so shouldn't be frightening in Kafka either. So those are all examples of events, but what are events actually? So an event is just something that's happened, okay? So innocent, right? It's just a tiny little thing. So a piece of information, ideally the smallest amount without too much excess, that tells you that something has occurred. So what do you need to do that? Well, you need to know when that thing happened, and that is really, really important. The timestamp is probably the only thing that you need to pay attention to in an event, when that thing happened, who or what was involved, and then any other supporting details. So getting back to me in this system, so I'm going to be collecting soil moisture readings, okay? So an event here should probably be, well, yesterday at 2:30 p.m., this plant here had a moisture level of 19%. Okay, so breaking that down, we have the timestamp, yesterday at 2:30 p.m., the who or what, so this plant right here, and then that supporting detail, that 19% moisture level. Great, that was pretty simple. It's not always that easy, but that one was pretty simple. Another really critical part of events is that they're meant to be immutable, and you have to just be okay with that right now, okay? It is just how it is. Events have described things that have already happened in the past. They have occurred, we cannot change them. I don't have a time machine, I'm sorry. You just gotta deal with that unfortunate fact of life, okay? So in this case, this event that we already generated, yesterday at 2:30 p.m., we had a 19% soil moisture level. That's unfortunate because that plant is very sad. That's a low moisture level. I would like to undo that fact because I want to be a good plant mom. That's my goal. But I can't go back and delete that event. I should not, or I should not go change that event. What I could do is just water the plant now, and in a few seconds, we'll generate another event that says maybe, all right, we have a 70% moisture level. Great. So that's what you want to do with events, right? You want to think of them as just incremental facts describing some entity in your system, and when you string them all along, we have this lovely timeline that describes that entity. Great. In this case, the moisture level of a particular plant. So based on what we just learned about events and the fact that Kafka enables streaming, I want the gears to start turning in your head about how this is actually a useful thing, okay? Where Kafka facilitates the movement of these immutable facts across your system and allows you to communicate these facts in a way that you maintain the integrity of that data. You know that's going to be the same no matter how many people tap into that data, and they can do whatever they want with it, which is pretty cool. But how does Kafka do that? And we have to look into some of the architecture and how Kafka stores your data to understand that. So it is a distributed platform, for better or for worse. Got a level set with that too. So the primary unit of storage in Kafka is called a topic, and topics just represent a single data set consisting of these events. You get data into Kafka, you write the data as key value pairs using clients called producers, and you can have as many of these as you want, writing to as many Kafka topics as you want, within reason, but really the sky's the limit. From there, more interestingly, we want to get the data out of Kafka, and you use separate clients called consumers. And again, you can have as many of these reading from as many Kafka topics as you want, within reason. But a couple other cool things about consumers, because this is where the magic happens. As you read through a Kafka topic, it would probably be useful to know where you've left off, right? Any application can go down for any reason, so I would probably want my consumer application to know which event it left off reading. And so Kafka has that functionality built into it using something called offsets. So consumers have the ability to keep track of those and commit them back to Kafka as metadata so that when they come back online, they can know where they left off. You can turn that functionality off, but it's very convenient in most cases. Consumers can work together, which is pretty cool. We can join them together as part of a consumer group. And so by doing so, they can parallelize the processing of events from a Kafka topic, which is really, really useful. But, and I think this is more interesting actually, is that consumers can work completely independent of one another and still get the same data from the same topic. Okay? And this is a really important distinguishing factor because when you're learning Kafka, for those of you who didn't raise your hand, it's easy to think of Kafka as some other similar technology, like a messaging queue. And a Kafka topic is not a queue. Although there are some features coming out that make it like a queue if you want it to. But generally, when data is consumed, nothing happens to it. It is there. It is durably stored on the Kafka topic until we clean it up at some point in time. But the reading of the data does not make it go away. Okay? Any number of consuming applications can read that same data and do something completely different with it. Kafka consumers are completely decoupled from the producers. They don't care about each other, they don't want to know about each other, and it's best that way. When you set up topics, you need to decide how many partitions are in that topic, and this is just breaking down that topic into further, tinier components. All right? And these partitions are themselves the immutable append-only logs where the events are actually stored on the cluster. And since Kafka is a distributed system, these partitions are going to be stored on different machines, ideally, and this allows us to provide better resilience and enable replication of that data. And I'm not going to get into that right now, but if you're curious, we can talk about it later. All right, back to the cool parts. That's your crash course on Kafka for those of you who did not raise your hands, and a refresher for everybody else. So, now we can get back to the pipeline here. What do we need to do to make this come together? Well, we need Kafka. So let's set that up. Easier said than done in most cases, but this was my first hardware project. I know you can't tell. I speak so confidently about it. It's like, I've been doing this for years. But one of my goals in actually building this project was to manage as little infrastructure as possible. Again, I'm lazy. I'm really lazy, and I wanted to focus on the actual hardware components that I had to build. And so I work for Confluent, full disclosure, and Confluent offers Kafka fully managed in the cloud. I thought it was a really great option for this project because I could just spin up a cluster in a couple seconds, and it was there and ready for me to use. If you want to follow along and build something cool like this, just have a Kafka cluster running somewhere. Okay, you can run in containers, VM, bare metal. I don't care where you're running it, just run a cluster. Cool. So I did that. Now let's build out the physical system, the cool part of this project with the Raspberry Pi. Here is everything you need. Kind of. This isn't a hardware conference. This isn't really a hardware talk. It kind of is, but I don't want to get too much into it because that could be a 3-hour session, right? But But I wanted to give you all the tools that you need if you wanted to build this on your own. Yes, I know this Raspberry Pi is overkill, but this was during the great Raspberry Pi shortage of 2021, and so this is what I could get. So all of that seems pretty normal, right? I want to call out the moisture sensors that I chose because there's a million of them out there that you could choose for some project like this. And so the ones I got, these were capacitive moisture sensors. They're a little more robust than other sensors you can get for the same thing. And they're I2C components. If you don't use or build hardware projects, you may not know, but I2C components, the way that they communicate with the Raspberry Pi is using a unique address. So I can have these sensors all wired to the breadboard over separate wires, and then we're going to take the same set of wires and wire that to the Raspberry Pi. So when the Raspberry Pi is requesting information from these sensors, it needs to explicitly call out which sensor it's trying to get that data from. Okay? So we need a unique address on those individual components to get the right data. And a lot of higher-end components let you set this per component. Mine were like $1.50. So it's cool because it did allow you to change the address of these sensors, but only to one of 4 values. Okay? So I bought like a dozen of these, okay? And I could only use 4 of them. I was a little sad. Half of them were broken because that's how it works in hardware. But I was a little upset. So tuck that away because this meant that I could only hook up 4 plants at a time to this system, which is kind of sad, but we'll get back to that. Okay, so here's a little bit of hand waving. I built my system. I crimped my own wires. It was fun. Hooked up these sensors to the Raspberry Pi and was ready to actually grab the data from the sensors. So all we had to do was move this into Kafka. So how do we do this? Well, before we get ahead of ourselves, my only advice that I give to people when they're starting any sort of project, I don't care if it's hardware related, I don't care if it's related to Kafka, there's going to be some data involved. And if you don't understand what data you're dealing with, you're going to set yourself up for failure. Or you're going to upset your stakeholders. That's even worse. Okay? So my only advice is to just sit down and think about the actual data that you need. And so as the only stakeholder, I probably didn't need to do this for as long as I did, but I sat down for about an hour or so to think about what do I want out of this project and what do I want out of it in the future, right? Are there some data fields that I could get right now that would help me out later, and so on. So all that meant is that I was able to boil down that thought process into a schema. Beautiful best practice. Please always use schemas. It'll save you some heartache. So sat down and generated this Avro schema for the readings that I wanted to capture from these moisture sensors. It's pretty simple. I could get the percentage moisture of the soil at that time. I could get temperature also, so I decided to bring that in. And I added a plant ID field that's going to help me later on for joining data onto our other data sets and keep track of the individual plants. Okay? So how do we get this data into Kafka? There are 2 main ways to do that. You can either use the Producer API or Kafka Connect. So the Producer API, this is your low-level sort of vanilla option for getting data into Kafka. Very reliable. And it's so great because it's available in all of your favorite languages and some of your least favorite, so you have options. You'll want to use the Producer API if you either own the application that's generating the data or you have access to it, which isn't always the case. So the other option is Kafka Connect. As the name implies, this is a way for you to connect data sources, some external sources, to Kafka. And also syncs later on, we'll get into. But the cool thing about it is that it's kind of plug and play. It's configuration driven. People have built many of these connectors. There's dozens, hundreds of them out there for sources and syncs. And you configure it to point to your data source. That could be an endpoint at the other end of an API. That could be some database or what have you. And then you run that, and it'll start programmatically grabbing that data and pushing it as events into Kafka for you. Okay? It's really good when you have data at rest, data that you don't own, again, that lives somewhere else external to your system, and you want to eventify it. I'm working on that word. Okay, we can workshop it. So what did I end up using in my case? Well, I own the Raspberry Pi. I am the only stakeholder. This is my application. So we're going to use the Producer API. And so I used the Confluent Kafka Python library. I'm sorry, I used Python. I know you can run Java on Raspberry Pi, I just haven't gotten there yet. But you'll recall that I need to reference every sensor by its unique address. And so I did huge red flag here. I hard-coded the mapping of moisture sensors to plant IDs. Again, tuck that away, we'll get back to it. And then within the script, every 30 seconds, I loop over that mapping, I fetch the moisture value, and I package it according to that schema and produce it to Kafka. So here's proof of that. And I will link to this code later on if you're curious and you want to use it for yourself. Yeah, there's nothing fancy up my sleeve here. I am using specifically a serializing producer. There is the option to use not a serializing producer, implying that you're not using a schema, so don't do that. So I can produce these readings into Kafka. At this point, we're capturing them at 30-second intervals, and great, that's being thrown into Kafka. But that's not enough for me to make sense of the data, okay? I need to understand the actual needs of my plants, and so I need some metadata to actually help me act on these readings. And so, again, after sitting down and thinking about it for a bit, I convinced myself that these were some fields that I would need to understand my plants a bit. So I created a schema. A lot of it is the names of the plants. They have given names, all of them. Scientific name, common name, just for fun. If I'm printing out this data, I want to know what plant I'm referencing. So we threw all that in there. And then the important stuff, we have the low and high temperature and moisture thresholds that plant is comfortable within. And this involved a lot of research on my part because generally most houseplants fall within the same range. They want to be between about 20 and like 65% moisture. Some of them fall outside of that. If you have a fiddle leaf fig, you know that they hate everything, and there's nothing that you can do to make them happy. But we can guess, okay? So I also added a plant ID number here to help me join onto the readings data later on, and help me keep track of these. All right, so let's get this data into Kafka. What are we going to do? Producer API or Kafka Connect? That's a hypothetical question. You don't have to answer that. And I do want to explain here. So for metadata, for reference data sets, data that is generally slow changing, that's a good candidate for data that might just live in a database, right? That's probably the right way to do this. But I'm lazy. And so I'm going to use the producer API, okay? I'm not going to waste my time putting this data into a database because I could just let it live in Kafka, right? And this decision mostly came down to the fact that I could only hook up 4 plants at a time, and I didn't need to waste my time writing all of this metadata at once, one by one, into some database. So this is what I went with, all right? So I wrote a similar script to what we saw before to just manually input that metadata according to the schema, serialize it according to that, and produce it into Kafka. But like I said, this was a lot of research for me in figuring out what thresholds my plants were actually comfortable within. And so I had to change this data a couple times. And that involved manually updating this script, updating the data that I was inputting, and running that again, which was kind of annoying. It's kind of a hassle. And again, I'm lazy, and I know I'm going to be doing this a lot moving forward, especially if I want to switch plants around, right? And so I figured I could get a little bit of help from Telegram. So I already wanted to have data sent to my phone through Telegram later on. So I started thinking about how could I use Telegram as a producer? And so how this would work is that, how many of you have heard about Telegram or use it? Good, okay, most of you have, great. How many of you know about its API? Not enough. It's so cool. Okay, this is like, I use it for all my random projects now. So it's a messaging app, for those of you who didn't raise your hands, like WhatsApp, WeChat, but the cool thing is that it has a very, very rich API around it. And so what you can do with that is you can register and create a bot. And when you do that, you receive an API key that you can then write a script to register that bot and write the processing code that you're going to use to have a conversation with that bot, how your bot reacts to conversations that users have with it, okay? So there's a really nice Python library for this, and so I figured we could go with that. So for any Telegram bot, you're going to follow pretty much the same process. You define a high-level conversation handler that just lays out how someone would have a conversation with this bot. Okay, the general fields that you're trying to collect and the different, responses you're trying to give to them, okay? So it's basically just a finite state machine, just outlining, what's next, okay? So here I am just outlining the high-level flow here. We're just capturing the plant ID followed by the individual details that I'd want. And diving into one of those message handlers, so here I've already prompted myself for the low moisture threshold. I'm going to grab that from user input, store it temporarily in state for the duration of this conversation, and then prompt for the next stage of the conversation. So at the end, we're forwarding to the moisture high stage of the conversation where we will collect that information. Before we forward it, I actually reply, and the bot replies and asks for that additional information. All right, so we keep doing this until I've collected all of the information as defined by my schema. Once I've done all of that, remember, all of this is stored as key values in temporary state for the duration of the conversation. So now I have everything. I just have to produce it to Kafka. And since this is within a Python script, again, I can just insert a serializing producer within that code and package it according to that schema and produce it to Kafka. Okay? So there's nothing really fancy up my sleeve. I did extract some of this boilerplate code into helper classes, but again, I can link to this code at the end. So what does this look like? When I run my bot, and I have a fun little conversation with it, it asks me what I want to do. I want to update my plant metadata, and then it prompts me for the information one by one. I have some defaults built in there if I want to use that as well. It confirms the metadata entry that I want to actually send to Kafka, and when I say yes, it sends it off. It'll retry if something happens, and then the data's in Kafka, and I don't have to touch my computer. It's beautiful. So I've succeeded in adding, or more importantly, updating old metadata for a given plant ID from my phone. But what's the point of that if I still have that hard-coded mapping of sensors to plant ID in my script? There is no point. You're right. So rather than have that be hard-coded on my collection script, I figured I could make that script a little more event-driven and get those mappings from Kafka. Okay? But to do that, we're going to need a little more information and a new schema. Okay? So here, these mappings, they're very simple, right? I just want to be able to store the sensor ID to plant ID, okay? And I want to be able to collect that from my phone. So very, very simple schema here. And then I'm going to follow pretty much the same process that I did for the updating metadata conversation handler. And I'm going to add a new one for the same bot that allows me to update mappings. The difference here is that I can actually, this is where it's safe to have a hard-coded mapping of those sensor IDs that are never going to change. Those are my options. And so I select those from a predefined list, and then I tell it which plant ID I want to have to map to that. Similar process, we're collecting that, serializing it according to that schema, and shipping it off to Kafka. Cool. So now all of the information that I actually need is in Kafka. This is perfect, okay? It only took half of the talk, okay? That's it. Now we could actually start doing things, but first we need to start using this information within our Raspberry Pi script, right? So we need to consume the data from that mappings topic. Cool. There's a couple ways to get data out of Kafka, Consumer API or Kafka Connect. You're going to follow much of the same considerations that you would for production of data. So generally, if you want to react to every event and maybe do something different with it, you're probably going to use the Consumer API. It's flexible, again, available in most languages that you want to use, and you're free to do with whatever you want with that data. On the other hand, if you're looking to move the data downstream to some database or a longer-term data store, then you're probably going to use Kafka Connect. Okay? So here we're going to use the Consumer API and add a consumer to that initial script, that collection script. A couple things to note here. So first of all, the mappings topic that I created to store those mappings, it's going to have one partition, and it's going to be compacted. What does that mean? A compacted topic is guaranteed to keep at least one value per key. Okay? And so why did I do that? Well, I don't really care what the sensors were mapped to before. I don't really need to know that. I just want to know which sensor is mapped to which plant right now. And so if I update and move plants around a bunch of times over the last week, I just want to really keep the latest value of that in my topic, and I'll let Kafka clean that up on its own, right? It also makes it a little faster for me to consume this data later on. And that's where we get into the next part, is that, okay, when I start up this script, my consumer first needs to populate this mapping of sensors to IDs, right? And so it's going to do that, but what if my application goes down for some reason? And it will. I restart my Raspberry Pi every couple days, okay? It's definitely going to go down. When it comes back up, generally, the default functionality is that it will start back up where it left off in the Kafka topic, right? Because it uses offsets, it stores those. So I want to turn those off. Because with my compacted topic, I'm not going to get, I might not update any of those mappings every couple days. And so I want to start from the earliest spot in the topic as possible. Okay? So I'm going to turn off these offset committing by doing enable auto commit false. Okay, this is a configuration within the consumer. So I want to turn that off. I'm never going to store any of my offsets. I'm never going to keep track of where I left off in that topic. And then I'm going to set auto offset reset to earliest. So auto offset reset says that when there isn't an offset for it stored in Kafka, then it's going to start at the earliest part of the topic when it can. Okay? And so what this means is that when I start up this script, my consumer is going to block. It's going to read all of the data from the Kafka topic, build up a mapping of 4 values, 4 sensors to 4 IDs, and then we'll start the collection script. At the end of every 30-second loop, we will also check again to see if there's any updates to that metadata, that mapping topic. Okay? So what this means is that if I want to swap plants around, when I update the mapping from my phone, within 30 seconds or sooner, we're going to have that populated in our collection script, and we'll see the right data being mapped in the Kafka cluster. So that's good. That's pretty event-driven. I'll take it for an at-home Kafka project. So first half of the pipeline is complete. It's fully event-driven. Moisture readings are being collected, thrown into Kafka, and we have means for producing new mappings and new metadata at my leisure, whenever I want. So now we can start making sense of this data using stream processing. So how do we do this? Well, first of all, I'm only going to look at your processing options within the Kafka ecosystem. There's a lot of other technologies that you can use outside of Kafka to do this. But the OG way in Kafka is going to be with the consumer and producer API, the things we've already been using. Okay? Same benefits apply. They're available in all your favorite languages. That's perfect. But to use them for stream processing, it's a complicated workflow. So you got to set up a consumer to consume from Kafka the data that you want to process. You do whatever transformations that you want, aggregations, what have you, and you set up a producer to produce it back to Kafka. That seems pretty simple, and for stateless processing, that is completely fine. You should do that. It's pretty simple, right? As soon as you add state into the mix, you've got a lot more to think about, okay? Specifically, what are you gonna do when your application inevitably goes down? Okay, where are you putting that state? Are you storing it somewhere on the local machine? Are you storing it somewhere else? Yeah, do you have like failover plans for that? You have a lot of things to consider, and in some use cases, it doesn't matter, and that's completely fine. But, you got to think about more. So if you're a sane person, you want to do some serious stream processing, you want to involve state, you're probably going to use one of the next 2 options. So the next one is Kafka Streams. So this is a purpose-built library in Java and Scala for stream processing, for stateful stream processing. So what you do is you define a topology of how you want to process the events that are flowing through Kafka Streams, using some of these options on the right here. And it's going to take the hassle of managing state off your hands. It's amazing. It's so good. And so what it does is when you spin up a number of Kafka Streams instances for the same application, and first of all, we're going to be able to parallelize the processing based on the number of partitions that are on your input stream of data. So that's pretty useful. And each instance is going to have some local state. So that's backed by rocksDB. And then we're also going to take that same state, and we're going to commit that to Kafka. We're going to store that in a Kafka topic. And so if your machine catches on fire, you lose everything. When you bring these instances back up, they will be able to start back up where they left off. That state has been durably stored in Kafka. Okay? Okay. That's really convenient too. If one machine goes down, we're going to rebalance those partitions that we were processing across those other remaining instances, and it's going to rebuild that state for you. So pretty useful. But if you don't want to do that, if you don't want to set up an entire application, or if you're a little lazy like me, the next option is probably going to be better. And so this is ksqlDB. So it's built on top of Kafka Streams. It's a SQL wrapper on top of that, right? You have access to the powerful stream processing that you can do with Kafka Streams, but all you have to do is write a couple SQL queries, which is pretty useful. So this is what we're going to use here today, a little more convenient, and I can also run it within Confluent Cloud. I don't have to run any applications on my own. So how do we process with ksqlDB? Well, the first thing you need to do is get the data into the application, okay? And you need to decide how your data is going to be represented to that streaming application. There are two main constructs in ksqlDB. We have tables, we have streams. Streams represent unbounded ongoing series of events. Tables, on the other hand, are a snapshot. They show the current state of the data in a topic in this application for a given key. So it effectively treats the data as though it's in a compact topic. It wants to show you the latest value per key. So let's look at that houseplant metadata first. This should be represented as a table, right? Especially if I'm updating information, if I'm changing the low threshold for some plant, I want that to be propagated as quickly as possible to the processing layer, right? I only want that latest value there. So we should represent this as a table. So we're going to use this very SQL-esque create table statement to define this. The biggest part that you need to focus on is which Kafka topic are we getting this data from? So I'm going to input the houseplant metadata topic where we're storing this. And this is what's going to be used to actually populate this table. The next important thing is defining the value format. So I created an Avro schema to define this data. And so I need to specify that here so that this consuming application knows how to get this information. But the really, really cool thing here, the benefit of sitting down and actually writing a schema and adhering to it, is that that schema, when we start writing it to Kafka, writing that data to Kafka, that schema is going to be stored in the schema registry, right? And so as a consumer, ksqlDB is going to see this value format as Avro, look at the Kafka topic, it's going to go look up that schema registry, and then it's going to use that schema to parse all the fields and their types. So I don't actually have to specify any fields here. I don't have to risk those typos. I'm the queen of typos. And so the only field that I actually have to specify is the key, right? What is the primary key? Because again, we're building a table and it needs to know which field we're actually getting rid of duplicates for and keeping the latest value for, all right? So I can take this SQL statement, I execute it within the Confluent Cloud console in the ksqlDB editor, and when I run that, we're going to start building up a table for us to use. All that data is going to be populated. So every time I update metadata, it's going to flow through and be updated in this table for us to use in our processing. So next, the readings data. Every message is relevant here. We want to be able to do something with it. So it's a stream. It's an unbounded series of events. So we're going to use a create stream statement that's going to look very similar to the create table statement we just saw. And again, we have all those perks of defining a schema. I don't have to specify any of the fields or the types. For consistency, I am also defining the ID field here as the key. All right, now we need to mesh these data sets together, okay? Because the readings aren't good enough on their own. We need to use the metadata to actually act on this information and do something with it. So here we are going to join this data together. Let's focus on the SQL statement first. So we're just joining two data sets. So we can use a select statement, select all the fields that we want from both data sets independently, both these topics, and join on the ID field. Great. We're using an inner join just to make sure I have all the data that I need. I should have it, but just in case. So if I took this select statement, just from select to the join, and I executed that in the ksqlDB editor, it's going to spit out what's currently in the topics. It'll execute this join and just spit everything out for me. That's not very useful. I mean, it's good to test the SQL and understand what we're working with, but I would like this data the result of this join to be stored somewhere, okay? And so that's where the create stream statement at the top comes into play. So by joining these two things together, now adding the create stream statement, I can say, I want to create a stream for me to use in the next stage of this processing. So we're going to store this data in there. This is the Kafka topic that I want to store it in Houseplant Readings Enriched. And we're also going to store it in this value format. So it's going to generate a schema for me according to that. And so, cool. I can take this create stream statement, have that select statement run against it. If I run this chunk, cool, it's going to create that stream for me. It's going to execute the join on all the data that's currently in that topic and append it to that stream. And then it's going to stop, which is okay for some use cases, but I want this to be long-living. I'm constantly generating data and sending it to that readings topic. And so I want to execute this join on every piece of data that comes in. And so I'm going to add emit changes to the end. That's a really important piece. So with emit changes, this indicates a push query, which says that whatever result is, the result of this query is going to be pushed to me as output. Anytime a new piece of data flows in on that incoming readings topic, we're going to execute the join, append it to this stream for us to use. And that's contrasted with what we just went over, which was a pull query, which is just pulling a finite result set to you as output. Okay? So I can execute this whole thing and ensure that every new piece of information is going to be joined and appended to that stream for me to use. So now we have all the information to actually make sense of this data and actually act on the information we have. So I want to summarize what I want to do here. I just want to know when my plants need to be watered. That's all that this is for. Okay? I just want to know when a plant has a low moisture reading, effectively, and then I want an alert on my phone. But these readings are being generated every 30 seconds, right? That's kind of a lot of messages. If my plant needs to be watered, I don't want to get a message every 30 seconds. I want data at that granularity for other analytics that I want to do, and I have so many plant things I can do at home. But in this case, I just want to know if my plant needs to be watered. And yeah, so how do I decide when is an appropriate time to send this? So I've changed this a couple times since I started the project, but again, we are generating the data every 30 seconds. And so I figured, okay, if I'm busy, if I'm in another country, if I'm out of the house at the office, maybe a 6-hour interval is a good enough time for me to receive an alert over, right? That gives me enough time to either go home from work and water my plant, or tell my partner to go water, and send him a picture and tell him which plant to water, right? I also noticed, as I was working with these very high-end sensors, that they're not perfect, right? The general trend is that, yeah, the moisture level goes down over time. It should. They're not sitting out in the rain, so unless I water them, it's not going to go up. But I'm going to get a lot of false low and false high readings. But again, that general trend is that moisture level goes down. So within a given 6-hour period, you're combining both these facts, within a given 6-hour period, it's probably good enough if, for a given plant, if I receive, 1 hour's worth of low readings. That feels like it's pretty serious, right? That plant has had enough low readings that maybe I should check on it, yeah? So with the readings being taken every 30 seconds, doing a little bit of simple math here, I should get at least 120 low readings within a 6-hour period before I send an alert. So this is the query that I wrote to achieve that, okay? A few key things to focus on. First of all, the most important part, I want to receive an alert at most every 6 hours. And so the first thing we're going to do for the data that we've enriched is we want to bucket it into windows, non-overlapping windows of size 6 hours. We have a little bit of a grace period in there, but generally the 6-hour part is the most important. All right, so already when the events come in, we're going to bucket it according to whatever window it falls in. Within that window, we're going to count the events where the moisture value on the reading was lower than the low moisture threshold, as determined by that plant metadata topic. When I get at least 120 of those, a result is going to be emitted. Okay? And note here that we're also grouping by plant ID, so this is within a 6-hour period per plant. I don't want to oversimplify this part, because it's easy to look at SQL and kind of forget that you're building a streaming application here and understanding what's going on with the state. So I want to clarify. When the enriched events flow into this query, first of all, we're going to bucket it according to that window, and we're going to conduct an aggregate, okay? And because we're conducting an aggregate, the output of this query is a table. So in real-time streaming applications, there's going to be a lot of incremental results. None of these are the final result. Within that 6-hour period, I'm counting up, 1, 2, 3, 4, right? Whenever we have a low reading. but we don't really want to send an alert on those. Okay? So we're going to be getting some incremental results output to this table. And so that's why it is a table, right? We want to update we want this to represent the latest value per key, which in this case is an aggregate of the window and the plant ID. Okay? So every time these events flow in, we're bucketing it, grouping it by the plant ID. We are incrementing the state. Every window and plant ID combo has a state associated with it. You can do a lot of things in that state, but in this case, we are just incrementing a counter and keeping track of that. And then whenever we breach that 120 readings threshold, that's when we're going to output an actual result here. But you might be asking yourself, rightfully so, what happens after we reach the 120th reading? Are we going to output a result every time? For 121, 122, am I going to get results every 30 seconds? Yes. And so that's why I included this cute little thing at the bottom, emit final. That's really, really important, because otherwise, what was the point? So with emit final, as opposed to emit changes, this says wait until this window has closed, wait until the grace period has ended, and then, if you emit a result, emit it. All right? So what this means is that per plant, within a 6-hour period, I am receiving at most one alert telling me to water that plant. So cool. All right. Now that's being generated to Kafka. I'm storing that in the Houseplant low readings topic. And so now all I have to do is just get that out of Kafka and use it, right? It's simple. And I want this to be received on my phone. So how do we do this with Telegram? Well, I had already created a bot. And when you get a bot, you get an API key that you can use to interact with that bot. When you start interacting with that bot, you can then identify the conversation ID that's unique to my phone interacting with that bot. Cool. So using that API key, the handy-dandy Telegram API, and the conversation ID, I can build up an endpoint that I can send data to my phone using. That's pretty convenient, right? And even more convenient is that there is a Kafka Connect HTTP sync connector. All that needs is an endpoint that you want to send the data to. So that's great. And even better, it gets better. It's fully managed in Confluent Cloud, so I didn't have to actually maintain this connector on any of my machines. It's just running for me in the cloud. So all I had to do was take that endpoint that I built up, use that in the configuration, point to the Kafka topic that I want to pull this data from, and I used a bit of regex to actually extract the relevant message that I want to send to my phone. Okay? So when I run this, any of the messages that appear in that low readings topic are going to be, we're going to extract that information and send it to my phone, and this is the message that I receive on my phone. See, I told you that given name was really useful here. It's just like a little more guilt-ridden, right? And so, cool, then I can go run off and water Bradley, because he's very sad, okay? So I'm pretty proud of this project. Like I said, it was my first hardware project, and I achieved my goal of bringing Kafka into my house, because who wouldn't want to do that, right? And thank you for coming along to experience this very self-serving project of mine, but you actually got something out of this, okay, I promise. I tricked you. You thought it was just fun, but you learned a lot about streaming data pipelines. You saw the different ways that you can get data into Kafka, more on the producer API side of things, but we heard about Kafka Connect. You were introduced at a high level to some of the ways that you can process in the Kafka ecosystem, starting with the consumer and producer API, Kafka streams, and then more specifically here with ksqlDB. And then we saw a bit about how to get data out of Kafka using the consumer API in that reading script and also Kafka Connect there at the end. So every streaming data pipeline that you build or will build is going to need some combination of these three things. And so at the very least, if you haven't started building stream data pipelines, you at least now have the tools or are aware of the tools that you need to help make that happen. So I hope that you will play around with Kafka if you haven't already, or if you do use Kafka, what's stopping you from building something annoying in your house with Kafka? Answer me that, okay? So if you're curious to see the source code, everything that I have running on the Raspberry Pi, here's my link tree. I also have a couple more resources there to Confluent Cloud and our Confluent Developer Portal, which has a lot of cool courses if you're looking to expand your knowledge on Kafka generally. So I hope you'll check it out. And I am at time, but I'm happy to take any questions. And as promised, here's my bribe, stickers. So Thank you for coming at the end of the day to see my session, and I hope we can chat. Thanks.